Good afternoon. This is Hakam Raisa, Technical Support Engineer at Navy Engineering and Agencies, sole distributor of COMSOL Multiphysics in the Arab countries. Welcome to COMSOL Multiphysics Mechanics module. Today we're going to talk about the module, what kind of features you can use, and perform a simple example at the end. To begin with, we can see the features in COMSOL Multiphysics module. When you have a solid mechanics module, the more features you can find if you add more other, different other modules. For example, if you have structural mechanics module by itself, you can find solid mechanics, shell, layered shells, and so on. But if you have something like AC/DC module, you have material restrictions, piezoelectricity. If you have also the fatigue module, add additional functionality and additional multiphysics to your suit. So basically, these are the features you can find under the structural mechanics node when you have some of the modules we'll talk about in this series. But for structural mechanics modules, the main features you can find is, for example, you can use it to analyze two-dimensional and three-dimensional structures. You can have analyze planes, membranes, shells, and so on. And also, you can have solid three-dimensional objects. You can analyze trusses and different wire and beam structures. You can analyze what's it called shells, thick and thin shells and plates. All of these can be used or can be found in the structural mechanics module. Under the structural mechanics module, we have different sub-modules which we're going to talk about in future sessions or future webinars. But for now, these are the basics we can find in the structural mechanics module. We have different types of analysis you can find in this module. For example, static analysis, parametric analysis, eigenfrequency, depth eigenfrequency, frequency response, transient viscoelastic, linear buckling, and all of these you can find in this module. You can also add a nonlinear structural mechanics submodule, so you can have isotropic elasticity, anisotropic elasticity, orthotropic, and you can simulate nonlinear material this way. As for the multiphysics, when combining structural mechanics module with other modules, for example, you can find the piezoelectric effect, acoustical structure interaction, thermal electric and structure interaction. So, for example, you're passing certain electrical current through a member, it heats up and deforms. So you have structural stresses and thermal stresses due to the electrical current passing through the member. We have also the fluid structure interaction by combining the fluid mechanics part of COMSOL with the structure mechanics and thermal structure interaction. Other than that, anything else you would like to couple with structure mechanics module can be done manually. You don't have to rely on the prepackaged only multiphysics in COMSOL multiphysics. You can do it by yourself as user-defined couplings. As for the demonstration for today, it's a simple bar necking demonstration, or dog bone as we call them. Basically, it's just a bar of a certain material, and this material is being pulled or displaced from one side, and based on that, you can see a certain necking at this domain. So this is what the result should look like. This is supposed to be a material, a bar made of certain material, for example, certain types of steel or polymer. When applying some certain tension forces, pulling it apart, what you get is necking at the middle before being cut into two pieces or split into two pieces. You have plastic, you can then plot the plastic deformation and elastic and plastic deformations, stress and strain plots, whatever you would like to extract from this model can be plotted then. In this case, since our model is axisymmetric around is a cylinder and axisymmetric around the center of axis in the center, we can draw it as a rectangle, and since it's symmetrical up and down, like the top and bottom are symmetrical, you can just draw a rectangle which is half the length of the whole bar and then replicate it into COMSOL. You don't have to draw the whole thing and compute it all together. So we can start by going to my COMSOL Multiphysics. And this is what it should look like when you start COMSOL Multiphysics. We start with Model Wizard, and then we can go to 2D axis symmetric. Under physics, you can select structure mechanics, but before that, I would like to just make sure that my licenses are up to, which is not, and select them all. Yeah. So we can go to structure mechanics. We can select solid mechanics, click add. Next, I'll go to study, select stationary, and click done. And my next step is to start with the parameters. I'm going to import the parameters from a pre-existing file. So these parameters are predefined. So you have the initial heat stress, saturation flow, stress, the bar length, radius, displacement of the bar itself, which we're going to use this parameter to modify in the study to increase it bit by bit until it reaches our like target or maximum extension or displacement in this case. So next we can go to our geometry. First we make it in millimeter, change the length unit to millimeter, and then start drawing it by going to geometry, rectangle. The width of this rectangle is going to be R0 from our parameters, and the height is going to be H0 over 2 since it's just half of the whole bar. After drawing it, you can see this rectangle, which is half of the bar, and if we rotate it around this red axis, it's going to create a cylinder, which is our end product. This would cut down on the mesh elements and the computation time to simplify the model further and make it run faster. Since you don't have to compute the whole three-dimensional model, you just compute a slice and rotate it around a 360 axis. Next, we can go to my solid mechanics, my physics, and I can go to physics. You can go to boundary conditions and then select pre-described displacement and edit the name to bottom, like that. So this is the pre-described displacement of the bottom part, which I'm going to select now. So it's boundary number 2. And then select in the Z direction, like that. Next, I can select another one, pre-described displacement. And this is one for the top boundary. So we can type top and then select our top boundary. The naming is just for us, so we can follow up later in the bottom. And you don't have to go through each and every boundary to know which boundary you selected. You can just note by name. And this one is going to be pre-described in the R direction and in the Z direction. And under U-note or the displacement will be from the parameters, which is delta. We will start by, if you go back to the parameter, we're going to start by 0 and then increase it later. So it's 0 now. Next, we're going to go to linear elastic material. I'm going to select plasticity. And then select large plastic strain. And then here, the isotropic hardening model, we're going to go with user-defined. And under user-defined, we make it from material, and then we're going to go create our own material. So under material, since we're missing now a material, we can go add a blank material. We can leave it as material 1, and since we only have one domain, we want to select this one. And the properties we'll have to fill manually. For the properties, the Young's modulus is going to be 206.9 gigapascal. And whenever I type unit, I can just put it between square brackets, and this way I don't have to convert it back and forth to SI or any other unit suffix. It's automatically converted here. I'm gonna go enter the rest of the properties. And under hardening function, I'm going to create a function which I'm going to call SIG_H. When I enter it now, it's not going to be understood because there is no function with this name yet, but I'm going to create it right now. So under the material, I'm going to go to the properties. Under it, I can create a function, analytical function. And in the expression, sorry, in the name or function name itself, I can call it SIG_H, which is the function, which is the name we used earlier. And under the expression, I can use this expression for it. And the argument is going to be EPE, which we used earlier. And we're entering the units for the argument and the function. And it should look like this. And this is what the function looks like when you plot it. You go to the material again. Go to elastoplastic material model. Go to property inputs, add one. And under the filter, we're going to filter for effective plastic strain. You can use the filter to search for this. Yes. So we have the effective plastic strain. And now if you go back to our material and then the properties, we can find that the hardening function is now correctly defined and it's not orange anymore. So we defined our material, we defined our physics. Let's just minimize them and the geometry. Now we can go to our mesh. Use the physics controlled mesh. Leave it as it is for now. We can just select the mesh size as finer and then create map mesh and build it. So this is what it should look like. Next, we can go to our study under stationary. We need first to show the default solver. Then we go to solution one, stationary solver, fully coupled. Under method, the method of termination, you're gonna use the double dog leg, just like that. Because this is a highly nonlinear problem, we need to change a little bit of settings in the study settings. As for the parametric sweep we are going to use, or the sweep we mentioned earlier for the delta in the parameters, you can go to solution to the stationary solver, go for study extension. I'm going to select auxiliary sweep and add the delta parameter and use the range which we used earlier, which is from 0 with an increment of 0.1 up to 7. And the unit should be in millimeters. So I'm going to change the unit to millimeter, like that. Other than that, everything is done, so we can just compute it. It will take like a minute or so. In the meantime, if you have a question, you can type it in the chat box and we can discuss it after the model finishes. This is going to take like another minute or 30 seconds. It's almost done. Yeah. So these are the default plots. So this is a stress plot. You can see that the material has extended, and while extending it, this section underwent some necking. And this is the section we defined displacement in the Z and R. So it's decreasing or increasing in radius. So if we compress it, it's going to buckle. If we extend it, it's going to shrink like that. But since it's just half a model, we can create a full model out of it. So this is the upper half, or this is the upper half we have. We can create a mirror at this boundary, and we can create the whole model. To do so, we can go to datasets, right click on it. We can use under more 3D dataset, we can select mirror, select the plane. The plane we're going to use is YX or XY at the 0. So now we have our plane like that. So if I go back to my stress plot, instead of having the data from dataset from revolution 2D1, we can use it from mirror 3D1. So it will look like that. So this is my model. For sure, I can change the colors, change the contours, whatever. But as you can see, the default plots has two plots in them. The surface one is for the von Mises stress, and the second one, I'm not sure what is it, what is this expression. It's for plastic strain. So this is the default expression they used. So you can see this is the default plot. I can cut into it, I can slice into it, I can change the kind of revolution I have for this plot. Whatever I want, I can do in these plots. So for example, in the revolution, instead of having it from negative 90 degrees to 225, for example, I can make it just negative 90 degrees to 0. It's a lamina, or to 90, just 1/4. So if I mirror this, mirroring just 1/4, and if I plot it, I'm going to plot just 1/4 of my rod, or I can plot it as a whole. So from this to 360. Yes. So if I plot it as again, it should be a whole rod now, like that. So this is how easy it is to use COMSOL multiphysics and do certain nonlinear structure mechanics analysis. It might be a little bit challenging when you come to the study settings, but you're going to get the hang of it when you dive deeper into the functionalities and different functionalities under the study settings and the physics itself.